Welcome to another Storm Crowd Factory Insights. This video is going to be a little different. I'm going to look at recreating the basic functionality of an Enigma cipher machine using Crowd software. The Enigma is a series of cipher machines developed in Germany between 1923 and 1945. Portable, battery-powered, and resembling a small typewriter, they were used during World War II by the German Army, Navy, and Air Force to encrypt and decrypt secret messages. I'm not going to go into the deep technical specifics of how an Enigma works. There are far better resources than me for that kind of info, which I have linked to below in this video. But essentially, the keys on an Enigma machine are wired to light bulbs in the panel above it. Rather than a straight connection, these wires pass through rotating discs, which have input and output pins for each letter. Inside the rotor, internal wiring reroutes the input pin to a different output pin. For example, the input for a letter A being connected to the output of a letter E. Depending on the type of Enigma machine, there are 3 or 4 of these rotors connected together so that the letters get jumbled up as it flows through the 3 rotors, off of the reflector, and then back through the rotors again. In addition, there is a plug board which further jumbles up the letters. Finally, the wires head to the lamp board, illuminating a final encrypted or decrypted letter. Now, the power of Enigma was that these rotors would rotate individually with each key press, meaning that there was no pattern to the encryption, and unless you knew the correct starting position of each of the rotors, you had very little hope of ever decrypting the message. The Enigma code was cracked and read initially by the Poles in 1932, and then by Bletchley Park in England, continuing and expanding on this work where they regularly read the German encrypted messages throughout the war. So, what does a World War II cipher machine have to do with VFX Crowds? Well, absolutely nothing. But I thought it would be fun to see if I could recreate the basic premise of the Enigma using only logic networks within Massive. For simplicity's sake, I'm going to ignore the plug board and the naval Enigma with its 4 rotors. So the first thing we need to do is capture the keyboard. Using an input node, I can capture the value of each key press, and by pressing each key, I get an ASCII value, where lowercase a has a value of 97, and b is 98, etc. Then what we want to do is have that transposed to a different letter to be displayed on our version of the light board, in this case, output nodes. So I'll go ahead and create a bunch of fuzz nodes to detect the specific key presses of A to Z. Okay, so here are all the ASCII values between 97 for A and 122 for Z. It's not that easy to read like this, so I'm just going to reorganize them into a QWERTY keyboard layout. Okay, now I can connect the keyboard input to all of the fuzz nodes. Okay, I'll also create the output nodes to mimic the light board for each letter. Of course, there's no point connecting directly the value of each key press to its corresponding light on the light board because we want to have some sort of encryption going on in the middle. And this is where the rotors come in on the real Enigma machines. So we're going to have to try and mimic that somehow. Quite a simple way to do that would be to create some logic that says if the A key has been pressed, then this value here becomes true. So let's see what happens if I keep pressing random keys. This isn't activating until I press A, and then it very briefly flashes red. And in its simplest form, we can then just wire that into a different light. So if I press A, then G becomes lit, and B, let's say, becomes P. One thing that's obviously very evident here is that the G is still staying on. So we want some sort of extra logic which turns off the previous key's light. Okay, so press A and G turns on, press B, G goes off, and P comes on. I can press A again, and it goes back to G. This is working now, and I could map all of these out to different random letters, and I would get a different set of letters for the word that I'm trying to encrypt. However, one very important thing about the Enigma is that every time you press the same letter, you get a different encrypted letter. Whereas if I keep pressing A, I'm keep getting the value G. So I need to create some extra logic that changes this value based on the rotor position, because the rotor will rotate every time I press a key on the original Enigma. Okay, so let's create a simple counter. So now that I'm detecting my key presses and created a counter, I now need to start mimicking the rotor rotating so that I get a different value for the same key being pressed over and over again. And to do that, I would just create an extra bit of logic underneath that says if I press A, I want to display C. And then the next time I press A, I want A to equal T. And then the third time, A would give me a Z. So I now need to detect which counter I'm currently running on. So I'll create one with a first key press, create two more. So this is 1. Second time we press a key, and then the third time we press a key. So if A is pressed and it's the first time it's pressed, then A should equal C. On the second time that A is pressed, A should equal T. And then on the third time that A is pressed, A should equal Z. Okay, so let's see what happens when I run this simulation and press A. So A, the first time I pressed it, A should equal C. Press A again, and it's not triggered. And I keep pressing, and it's still not triggering. And that's because I haven't connected these extra rows. So if I connect these rows here, that's 1. This value should be 2. And finally, value 3. So now press A. A will equal C. Press A is now shifted to the second row, and A will equal T. And then 3, A will equal Z. So A will go to C, and then A goes to T, and then A goes to Z. So let's see what that does. Press A once, we get a C. Press A again, we get a T, and press A for third time, we get a Z. Okay, so I've just tidied this up a little bit and created some fuzz nodes and on-off switches just so that when I now start typing, my lights are staying on. To make things a little bit cleaner, I can just group all of these and put them into their own little macro. We'll call this output. So this is where our output is going to be processed. And then I can connect these values to our lamps. So I'll just connect these up directly. Okay, so now I've got my output processing module where the encrypted letter will get distributed out to the different lamps. Now, obviously, I only have 3 options for encrypting a letter, and it's only A. So I need to build out these values to create more random values for A. And if we're going to mimic the real Enigma, then I need to give 26 variations per letter. So let's try and do a bunch of variations for the different letters as well. So here is 26 variations of A, and I can then feed that into my encrypted letter and keep pressing A, and each time it gives a different result. And more importantly, you'll notice if you look at these encrypted values, it never shows up as A, because that was one of the weaknesses and flaws in the original Enigma, was that no letter could ever encode itself to itself. So A would never appear as A, which was one of the ways that that they managed to break Enigma. Okay, so you can obviously see that this is 26 variations of A. We now need to do 25 other random letters to match for the other key presses. So here we have every single letter now mapped, with each letter having 26 variations, and this is how it looks. So essentially this here is the internal wiring of a single rotor on the Enigma machine. I can now connect these all up to the output node. Okay, so now this represents every letter on the keyboard that is being read in, and then for each letter it's generating a different letter each time that key is pressed. All of this here now represents the internal wiring of a real Enigma rotor. If we take a closer look, you can see that for each key, here's A, B, C, each of them have their own encryptions. Now, one of the complicated things that we had to do here was not only create an encryption of whenever you press J, for example, it would create H to light up on the plug board. You also need to be able to get back from H to decode the message. If we go back here and look, and if we pressed H, that would generate an I. That's the encoding, and then that's the decoding. Let's pick a different example. If we press H on the 8th rotor turn, we get a V. And then if we press a V on the 8th rotor turn, we get back to the H. So that's how you can use the same Enigma machine to decode and encode without having to change and have a separate mode. You just need to know the original orders of which rows you're starting the Enigma wheels from, because you wouldn't always start from the first position. You would randomize daily or sometimes even hourly the rotor position. Okay, so now we have this mass of wiring. I am going to add this in to its own macro. This is going to be rotor 1. Okay, this section here is going to be also a little macro, and this is going to be my counter. So let's just type in, for example, hello. So run the simulation, just reset it. So we're now starting at position 0. Press H and I get an I. So if we're trying to write hello, the first letter when I type H, I get an I. An E, I get an L. If I press an L, I get a B. L again, I get a D. And then finally, the O, I get an A. Here's my clear text, and here's my encrypted message, which I would then send by Morse code or whatever. Now let's say that we've received ILBSA and we want to decode it. With my simulation still running, if I press I, then I get an L. The reason why that's not converted back is that I'm currently not on the first row. I'm currently on the 6th turn of the rotor. So I need to reset that back. And now I can type I gives me H, L gives me E, B gives me L, S gives me N, and A gives me O. So clearly there's something not quite right here. I'm almost getting my message, but N is not. So the input letter is 110. And if we go back to our ASCII, 110 is showing N. So we have not encrypted the right value here. So let's go into our rotor and read what value we're getting. The 1, 2, 3, 4th value for N that's here. And it should be N equals S, and therefore S equals N. So we need to go further back because that is a correct encryption from S and N. But it's L that shouldn't have created an S. So if we go back to L on the 4th value, it should have decrypted the value D. So it's given a value of 100, which in the ASCII table is D. And then if it had given a D and we'd have decrypted on the 4th rotor for D, that would have given an L. So I'm going to reset and try and encode the original message again. So press H and that gives an I. So H is encrypted and gives me an I. An E will then give me an L. an L will give me a B, and then press L again, and it should give me a D. So D is being output here. So let's go down here and we see that 100, the ASCII value of 100 is being output. D is now showing as D. H gives me I. E gives me L. L gives me a B. L gives me a D. O gives me an A. Can reset. Type in I, gives me an H. L gives me an E. B gives me an L. D gives me another L. And then A gives me an O. Alright, so let's use a virtual Enigma, which is quite fun to play around with, to encode a message, and we'll use our Enigma to decode it. So I'm just going to type out a simple 3-word message, which will be storm crowd factory. I want to include some spaces in there, but you notice that there is no spacebar on the Enigma machine, nor is there on our Enigma machine. So I'm going to replace those spaces with an X, and then at the end, to signify the end of the message, I'm going to put $X. Okay, so let's see what encrypted values the Enigma gives us. So S gives us a J, T gives us a Z, O gives us an N, R gives us a U, and M gives us an H. And then for X, we get an S. Then the second word, C, is A, R is T, O is M, W, J, D is F. Then another X for space, and that's an I. Then F is K, A is T, a C is a Y, a T is a W, an O, a Z, an R is an O, and then a Y is an N. And then I want to do my 2 X's to end with, so that's a U and a Q. So U and Q. Okay, so now let's take this encrypted code over to our Enigma and see what we get. Run the simulation and start typing. So a J gives me an S, a Z gives me a T, an N gives me an O, U, an R, H, an M, an S gives me an X. Well, I'm going to put that as uppercase because it might possibly be a space. Then an A gives me a C, T gives me an R, M is an O, J is a W, and F is a D, I is an X, and then K is an F, T an A, Y is a C, W is a T, Z an O, and O is an R, and N is a Y, and then a U is an X, and then a Q is another X. Okay, so there we are. We have Storm, X Crowd, X Factory, XX. So now that I have one rotor working in my Enigma machine, I'm going to add another 2 rotors. And rather than going through the whole process again, I'm just going to use a Python script to recreate the new rotors with their correct settings. So here are my 2 new rotors, all created with their encryption logic, different to the first rotor. And what I need to do now is connect them in so that the letters will pass through each rotor and then to the output module. So the output of rotor 1 will go into the input of rotor 2, and the output of rotor 2 goes to the input of rotor 3. And then finally the output of rotor 3 will go to my output panel. So the last thing I want to do is add the rotor settings, which can be changed so that the encryption is not the same every time you use the Enigma machine. So I'll just create 3 input nodes and create those as rotor 1 setting, rotor 2 setting, and rotor 3 setting. And then next I will just create some AND logic which will add the rotor setting to the current counter. So now I have these settings which are the starting positions of each of the rotor, so essentially adding to the counter, so that if I set my initial setting for rotor 1 at 5 and then for the very first time press the A key, then it will be using the encryption from position 5, not from position 1. So there you have it, an utterly pointless and ridiculous use of crowd software to create a single rotored Enigma cipher machine. Thanks for watching.